right, this is chapter 5.4, spring potential. We're going to talk about spring energy. Today we're going to talk about Hooke's law, which has to do with the spring constant, and the potential energy of a spring. And that's like the energy that it's stored when you squish the spring into it. So potential energy of the spring. This constant is called the spring constant. It is a lowercase k. Basically, it's how springy is the spring. It's based on the material it's made out of, how many coils, how big are the coils. And this Hooke's law is force is equal to negative kx, where F in this case is the restoring force, and it is in the opposite direction of x. That's what the negative means. Equation just a little bit more. F, the restoring force, means that when you push the spring in, it's applying a force back to where it started, right? So here's the spring, and you push it in, it wants to go back to that. So that's the force that's causing it to go back to what we call equilibrium. It's the spot without pushing it in. So that's what they mean by restoring. It's restoring it back to its original length. This negative, we pretty much ignore the negative for all of our stuff, because when we're doing free body diagrams, we put the direction on the force. So you don't really need to put this negative in here. So we can use just Hooke's law as F equals kx. We just need to know that the force is in the opposite direction when you push it. So if you're pushing the spring in, then the direction you pushed it was this way, but the force is going to be in the opposite direction. Yes.
So why do springs try to get back to the normal?
Because they're springy.
Because everything wants to reach
equilibrium. For the most part, it's just like any sort of elastic rubber band. Okay. You stretch it, it wants to go back to its original form. I even have a lovely spring example here.
Slinky.
Yeah. So it wants to stay here, and if I push it up, it's going to try to go back down, but it's going to have so much extra energy that it's going to go past that point. So you're going to see some sort of equilibrium point in between, because it'll oscillate around. And we'll talk about this more next semester, a simple harmonic oscillator.
Are we doing a quick live outside, or just down the stairs?
No. That would be fun, but every time I do that to a slinky, it breaks it, and I only have one slinky. Okay, so potential energy of a spring. It is elastic potential energy or spring potential energy. So either US or PES. Your book uses PE. I use U because I did physics in college, and that's what they use. I almost said I'm a physicist, but not really. Technically, not that right. It's equal to 1/2 kx squared, which looks a lot like 1/2 mv squared, right? Notice that x doesn't matter if it's pushed this way or pushed that way. It is squared, so it won't really matter whether you push it one way or the other. And that's mostly because energy, remember, negative energy means it was taken out, and positive energy was put into the system. So if you push this, doesn't matter left or right, you're still adding energy into the system. So that squared gets rid of that negativeness.
It's time for a question.
Time for a question? I think I started putting the questions all at the end because I never know if we're going to get through all the stuff or not. So there are questions. Not for a little bit. No? I still see some red. Here's a picture. You can see that before the spring is touched, it is at x equals 0, which we call the equilibrium point. In this case, the spring has no energy. Zero energy. If we do work on the spring by pushing it, we're taking our golden grams that we ate in the morning that's stored in our body, and we're adding energy into the spring. We're doing work on it, transferring that energy into the spring. It's now stored in the spring as a spring potential energy, so elastic potential energy. And that's because we have basically pushed it in x length. In C, we have released the block, and this potential energy has been transferred into the block as kinetic energy. And notice that it's at 0 again. So in a perfect world, which we do not live in a perfect world, but in a perfect world with no air resistance and no friction, you pull this, let's say that it sits like that. If we pull this spring out and we let it go, it should oscillate back and forth between where it started. So if we push it in with a block, here's my duck. We push it in with a block, so here's where it sits. We push it in with a block, it should, as soon as it reaches equilibrium again, send the duck off in this direction and not oscillate anymore, because all the energy was transferred into the duck to get it to move. But what you actually see is that it doesn't actually reach equilibrium because of friction. It slows down a little bit. It releases the duck. Some of that energy is left in the spring, so after it hits, you're going to see it oscillate just a little bit. But in a perfect world, it wouldn't do that. Okay, everybody's good with this slide? All right, so let's expand the work energy theorem to include a spring. This is pretty easy because we know conservative. In a conservative system, what's our energy look like?
Energy initial equals energy final.
Good. Energy initial equals energy final. That means that the initial kinetic energy should equal or added to the potential energy initial plus maybe the potential elastic or the spring initial. So let's say that this is mgh, right? Our gravitational initial, our spring initial. This all should equal the final kinetic energy plus the gravitational potential energy plus the spring potential energy afterwards. Final. So we can kind of simplify this a little bit into just potential energy U instead of saying UG and U spring. But if you have both, you'll have like springs hanging from the ceiling. So depending on what's going on in your system, it can have both gravitational potential energy and elastic potential energy. Hello? Yes? Mm-hmm. Sure, do you want to talk to her? Okay, forget it, it's for you. You're a VIP now. You get phone calls straight to my class. Hello?
No, you need to fill out the form? No, I think you put it in your desk, like somewhere under your desk, on one of the drawers.
That's good. All right, so that's pretty much what I wrote on the board.
You're welcome. Bye.
So I wrote this on the board. You shouldn't need that. But it's an expanded one. And to do this for a non-conservative, it's pretty much the exact same thing that we did before. You just add that spring stuff in there. Conservative. So now any change in energy, work is going to equal all this nonsense. Okay, final plus UG final plus U spring final minus initial. There you go. So that would be for one that loses energy. That would be like a friction, where your work is going to be frictional force d cosine theta. And technically, your theta, if it's friction, should be 180. All right, so here's my spring example for you. It says a 4-kilogram box is attached to the end of a spring. The spring hangs from the ceiling with the center of the box at 10 centimeters from the ceiling. The spring is compressed 7 centimeters. What's the max velocity? Where does it have the maximum velocity? And where does it have the minimum velocity? So 2 of those things, B and C, are pretty much conceptual. Does this mean conceptual now? Conceptual. Just trying to figure you out.
No, I just
Okay, cool.
nothing
All
more.
right, does anybody need the board anymore? No? I can erase it. Okay. Yay me. Okay. We have a 4-kilogram box. Our mass is 4 kilograms. It is hanging from the ceiling. It is pushed 7 centimeters up towards the ceiling. So basically X, this is X, is 7 centimeters. Now the end of this is a box. So the box is hanging in the middle. So this is our box right here. And it says it's hanging in the middle. So that's 7 centimeters. So what you want to do is draw a free body diagram on this. That might help a little bit. I don't know how much help it will actually be, but basically you'll end up with mg down and the spring force up. Actually, in this case, the spring force would be pushing it down because it's trying to restore its equilibrium. So spring force is also down. Spring. And that's Hooke's law. So we know that it's going to go this way. Once we let this thing go, what's going to happen to it? It's going to go down, right? So then it's going to go here. And you're going to have spring. And then what's going to happen to it? What's going to happen? It's going to snap? No. What did you say? Spring. It is at equilibrium here. What goes next? So here it has potential energy. It has kinetic energy here. So where's that kinetic energy going at this point? Go ahead, Nick. Good. It's going to overshoot it. Do you know how far it's going to overshoot it?
In a frictionless swirl where the spring is perfect and all, probably 7 centimeters.
7 centimeters, yeah. So it's going to go over 7 centimeters. Well, it's going to go to 7 centimeters. Here. Sorry, this should be 7 centimeters like that.
Then again, if the world's perfect physicist would be out of the job.
All these are the main jokes of physicists. I can't get it all right. All of them. So at this point, basically you have mg down, right? Your spring force is 0 because it's at equilibrium. And then here you're going to have the spring force up and mg down. So it's got a fight graph. That's your forces on this. So what kind of energy does it have here at A?
Oh God, that is
Potential.
Potential energy. And what else?
Spring.
No static. No spring there.
And gravity. So it has potential energy due to gravity as well, because it has a height. Okay, what kind of energy does it have here?
Kinetic.
Gravity and kinetic. Good. Okay, and what kind of energy does it have here?
Gravity and spring.
Depends on where you define your 0 point at. So if you define this as your 0, if you say height equals 0 here, or y equals 0, depending on what you're using, then it would have no potential, gravitational. But what else would it have? Spring, right? Potential energy due to spring. So notice that no kinetic energy, no kinetic energy. So where is its minimum velocity at? The outside points. Either the highest point or the lowest point in this case. That means where it's going the fastest. Right in the center. So here is going to be the maximum. So B basically says B max at equilibrium, and C V equals 0 at top and bottom. Okay, so now let's figure out what A is. What are we going to do to find A? Is it a conserved system?
Yes.
Okay. In a conserved system, what's the energy look like?
Actually, wait, it doesn't really specify.
Same.
It's
Initially.
initial equals final. But we don't really have initial and final. We have like A and B and C.
Wait, what if you just do if you don't specify? Because something we said
If it doesn't specify, you can assume no friction.
Thank God.
Yeah. I wrote this question. Usually it specifies. Okay, so that means energy at A. So we go potential energy of the spring at A plus the gravitational potential energy of the box at A should equal the kinetic energy at B plus the potential energy at B, potential gravitational at B. Now, if we got really excited, we could even go all the way down to C, and we could say the potential energy of the spring at C. So it doesn't really matter which one you set equal to each other, because they all equal each other. You just isolate two of those and solve. I'll do it the hard way. We're just going to look at this part in order to solve for our velocity. This is the potential energy of the spring at A. This would be 1/2 kx squared plus mgh. These are both at A. This is going to equal the kinetic energy at B, so 1/2 mvb squared, plus the gravitational potential energy at B, so mgh at B. And you can use H or Y. I use H because I've always seen it as H. I think your book uses Y. Y is probably the better variable here, but old habits, you know.
Well, it is a good day today.
So if this is 7 centimeters, and this is 7 centimeters, what is our HA? 14.
Yeah.
14 centimeters, which is what? 0.14? Our mass was 4 times 9.8. Now, even though the height is 14 centimeters, what's our x
0.
at A?
Oh,
It's going to be 7. So 1/2. They don't give a spring constant. That's terrible writing problems. What kind of spring constant do you want to give this thing?
Better copy one.
40. It's more like 400. They're pretty big. They're like 2,000 is a fairly common spring constant. So we'll do like 400, and it's newtons per meters. Sorry, I should have given you that. That's my bad. Although I guess we could have figured it out.
with the.
Yeah, with that we could have figured out the spring. I don't want to do that. It's too much work. Okay, so 400, 7 centimeters, so 0.07 squared equals 1/2. Mass is 4. We're looking for VB plus 4 times 9.8 times 0.7.
Where did you get 0.4?
0.14 or 4?
Or yeah, 0.14.
0.14 is the height, since I said this is my 0.7, and 7 would make it 14.
Okay.
And then, but the distance between equilibrium and where it's at is only 7. I don't know, that spring constant is kind of bugging me. Maybe I should do it. Too much work. Too much work. They'll give it to you. Okay, do we have an answer for VB, or you want me to do it?
It's actually 560.
560?
Yeah.
I gotta change it on the board. Figured it out. Oh. 6.86 on this side. Let me know if you get something different. Oh, 7.4. Okay, and that would be its velocity at V, or the equilibrium point, which is the maximum velocity. What if I wanted to find how fast it's going, like, right here? What kind of energy does it have right here?
Potential and potential gravity.
Potential gravity, potential spring, and kinetic. So all 3 of them. So if you knew how much energy it started with, you could set it equal to all 3 of those things added together and then solve for the velocity at that point. It's just easier. The equations simplify when you look at it at equilibrium because you don't have that spring potential energy anymore. Okay, are you guys ready for your clicker questions? Not yet. Nina's still writing. We'll wait. I'll stop this.